if it just goes off, if it's a standby, just hit this red button again. It'll record it. Okay. So this is the first problem. They give you a motor at A, and they give you this shaft, and they ask you to find the minimum diameter. So you want to find this diameter over here. And they give you the angle of twist from A to B has to be less than 1.5 degrees. Whenever you have an angle of twist, you have to convert it into radians. So you have to multiply by pi over 180. So first you should convert this. And they give you also the shear constraint. So you're going to get two different diameters, one from the shear constraint and one from the angle of twist. Okay? All right, so what you want to do first is draw a free body diagram. This is A, B, this is C, and this is D. All right, so nothing really is happening between C and D. But after that, if you cut it over here, if you draw a free body diagram from here to D, it looks like this. All right, so you got this shaft over here. And they give you the torque at C. It's 500 newtons, right? So what does the torque have to be over here? It's in equilibrium. What? 500, yeah. So it's 500 newton meters. Okay, so this is the free body diagram from, I'll call it from B to D. But it's not at B, it's a little before B. B to D. Alright, so what does a free body diagram look like if you cut it over here? Alright. And I'll call this from A to D. But it's before A, okay? Okay, so we got the 500 newton meters, and then we also got the torque at B is 300 newton meters. Okay, so what does this torque have to be over here if it's in equilibrium? You got two torques. One that's 300 that's going counterclockwise, and another that's going counterclockwise that's 500 newton meters. So this has to oppose these two. So what does this one have to be? 800, yeah. So this is 800 newton meters. There goes the chart. Okay. All right. So look, that's a free body diagram of this shaft. So you're going to need this to work with these constraints. Okay. They give you. Let's work with the shear constraint first. They give you the maximum shear. So if they give you the maximum shear, you're going to have to use a maximum torque. Doesn't that make sense? So you're going to have to use this free body diagram. So let me erase this. We don't need this anymore. All right. Oh, and this shaft is just a single shaft. The diameters are the same throughout the whole thing. Okay, so we don't need this anymore. So tau max is going to occur over here. Okay. So tau max is equal to TR over J, right? Okay, so we're looking for this quantity over here, the radius, but we want to find the diameter. Once we find the radius, we know the diameter. So we're looking for that. So let's rearrange this. We have tau max times J is equal to TR, and R is equal to tau max times J over T. Okay, so we know this also. Whoa, actually this depends on R too, so let me do this over. Okay, so we know J is equal to pi over 2 R to the fourth, right? So these r's are going to cancel. So you have tau max is equal to t r over pi over 2r to the 4th. So these r's cancel. So you have tau max is equal to 2t over pi r cubed, right? You guys agree? So you can move this to the other side. So you have r is equal to 2t over pi times tau max, all raised to the 1/3. You guys follow? All right, so we know the torque, the maximum torque is going to be 800 Newton meters when you cut it over here. You know tau max, they give it to you in the problem. It's 60 MPa, and these are just constants. Okay, so you can solve for the radius. All right, so the radius is 0.0204 meters, and then from this you could get the diameter. Okay, the diameter is just double this, so it's 0.0408 meters. All right, so this is from the shear constraint, but now we have to check the angle of twist constraint. Okay, so they give you the angle of twist. So that's one diameter you're going to get. You're going to get another diameter, and then you're going to have to choose a bigger diameter because you don't want this to fit. Okay. Can I erase this?
Wait, which torque did you use?
Oh, I use this constraint right here, tau max.
Oh,
Okay, and then next I'm going to use this constraint over here, the angle of twist.
Did you just do for the torque though? Did you just do the summation on the whole rod?
Yeah. You weren't paying attention?
No, I did. I just used
Okay.
two body diagrams.
Yeah, I did two free body diagrams to show you. I cut it here and here. Over here it's going to be 500 Newton meters. Over here it's going to be 800. So use a bigger one because that's going to produce the maximum tau, right? 800 opposed to 500. 800 is larger, and the torque's on top. Because remember, tau is equal to the torque times the radius over j. So you use a bigger number, and then you get the bigger shear stress.
What problem is this?
Oh. It's 3.46. Okay. All right. So now we have to get rid of this because we have to find the next diameter. Okay, so now we have to use the angle of twist constraint. Okay, so this gives you the angle of twist from A to D. So this over here is going to twist this much. Okay, and remember I told you this has to be in radians, not degrees. So first you have to convert that into radians. So BAD is equal to 1.5 degrees multiplied by pi over 180. This will convert into radians. What is that equal to?
It's 1.5 or 15? 1.5 or 15?
Oh, it's 1.5. Sorry. Yeah, it's 1.5. All right, so this gives you 0.02618 radians. Okay, so what you have to understand is that these two rods are going to twist. I mean, this is one complete rod, but there's sections of the rods that are going to twist, and they're going to add up. So this rod is going to twist because there's a torque on it, and so is this one. So there's two. There's basically, you guys get what I'm saying? There's one complete rod, but there's two sections that are going to add up to this theta, VAD, the angle of twist. So you have the angle of twist of this rod over here, plus the angle of twist of this rod over here is going to equal this value over here, multiplied by pi over 180. Okay, so you have phi BC plus phi BA is equal to this phi AD. Okay, so we want the radius out of this, right? And then we're going to get the diameter. So we know this and this. So this is equal to the torque times the length, EL over JG. Yeah. JG. Okay. So this is for rod BC, and this is, whoops, for rod BA. Wait. Yeah, that's right, right? Yeah. Okay. All right. This is going to have the radius of J, and this is equal. This is known. We already have this value over here. So this is equal to BAD. Okay. Okay. So this is going to have the radius in it. We know this. It's given in the problem. It's 77 GPa. We know the lengths of BC and we know the lengths of BA. So this is 6 meters, this is 4 meters, 0.6 meters, 0.4 meters. So we know this, we know this, we know this, we know this, and we know the torque. Okay, we know the torque in each section. I drew a free body diagram before to show you the torque in each section. You know what's the torque in this section and what's the torque in this section? Let's start with this one. This is what? This is, no, this is this section. This is 500 and this is 800. Yeah. So you knew what, I know you know what I was trying to say. Yeah, okay, that's why I drew the free body diagram before. So what you could do is, this is all one complete rod. So this J is equal to this J, they're the same. So you could factor it out, move it to this side. So you got J is equal to TL over B A D times G plus T, this is for rod BC, and this is TL over BAD times G, and this is rod BA, yeah, and that's it. Okay. This is G. Okay. So we said we know this and we know this. This over here, BC, this is 500 Newton meters. This is 800 Newton meters. And we know this length over here. This length over here is BC, where is it? Okay, 0.6 meters. And this is over here, 0.4 meters. Okay, and G's the same, it's just 77 GPa. So we could find the value for J, but you could simplify this further. You know J is pi over 2 times r to the 4th. You can move the pi over 2 to this side. Okay, let me rearrange that and stop. Alright, so we said J is pi over 2 r to the 4th, which is equal to TL over B AD times G, and this is BC plus TL over BAD times G, and this is rod BA. Alright, so you can you can multiply by 2, and then you can divide by pi for each one, and then take the 4th root, 1/4 root. Okay, so I don't have to do that, right? I can just give you the answer at this point. Okay, so I guess that's a yes. All right, R is equal to 0.02104 meters. Okay, so this is a radius, so the diameter is double that. So it's 0.0421 meters. And you'll notice this diameter is larger than the previous diameter, so you take this solution right here. Or you could write it as D is equal to 442.1 millimeters. Either answer is acceptable.
Well, you take the bigger one, right?
Yeah, the other one you'll notice is smaller.
Oh wait, its radius is 0.021, and then what's that? Like an alpha?
This?
No, the radius.
Wait, what are you talking about?
I just can't read the number there.
104.
It's just 104.
Oh, it's 0.0421 meters.
Sorry. The radius, not the diameter.
How did I
The
get
R,
to
it's just
104?
it's just 104. It's just like the 0 before.
So 0.021 and then it's what?
This is double. This is double.
Right.
The diameter is double the radius.
Right.
So you
Alright,
just
okay.
multiply this by 2.
Alright, but what's that thing to have after it?
Oh, this meters.
No, the thing between the two.
Oh man.
It looks like an absolute value of alpha.
Mashed together.
This?
Yeah, that thing.
Oh, this is a 4.
Oh, okay. Alright.
Oh, sorry. Oh no, sorry. Whoops. I have to write meter.
It's like shoot or shoot. No, shoot or shoot like this. No, I'm saying there's no shooters instead.
Okay.
Yeah.
I have to make sure he doesn't put this one on the exam, because I actually did a problem that he didn't assign, so I have to check it. Yeah.
Don't tell them.
Don't tell them. Alright, so this is, they give you the torque, this is 12.5 kips times an inch, and they give you the lengths of these rods. This is 12 inches, this is 18 inches, this is point A, this is B, and this is C. And they give you this rod is aluminum, I'll just call it AL. And they give you this rod is brass, I'll call it B. Okay, or brass. And they give you the diameters. The diameter of this rod is 2 inches, and they give you the diameter of this rod, DAB, which is equal to 1.5 inches. Okay. Did I put everything? All right. Okay, so they give you in this problem, they give you the modulus of the shear modulus for aluminum is 3.7 times 10 to the 6 psi, and they give you also the shear modulus for brass is equal to 5.6 times 10 to the 6 psi. And what else do they give you? That's it. And they ask to find the shear stress in rod AB and the shear stress in rod BC. Okay. All right. So they want the shear stress in both of these. So they give you the torque, and this is statically indeterminate. So first you want to draw a free body diagram of this whole thing, of rod ABC, to know what's going on. So you could use statics, and you'll notice that statics isn't going to help you in this case. Nice. Wait, you're telling me what Gupta taught me was useless? No, it's not useless. Okay. It's useful. It's just like in the beginning you can't get anything out of it, but after you can get something out of it. Okay, so this is equal to 12.5 kips times an inch. So we want to know what kind of torque this rod is receiving and what kind of torque this rod is receiving. We don't know. So I'll call this reaction A. So I'll call this TA, and this TC, okay? Because we don't know these torques, but we would like to know them because then we could find the shear stress in each rod, okay? So this is what the free body diagram looks like. Notice these are in the opposite direction for this torque, right? Because it's trying to oppose this torque. So if you drew it in the wrong direction, your answer probably is going to be wrong. Okay, I didn't try it, but okay. So what do we get from statics if we sum the torques? Counterclockwise is always positive. You get TA plus TC is equal to T, the torque. And we know that torque, that's 12.5 kilonewtons. You can't do anything with this, so we're going to have to use mechanics and materials. What you have to know about this is the angle of twist over here. So this is going to be twisting, right? So there's going to be an angle of twist over here, but it's going to be equal at this point. This rod over here is the angle of twist for this rod is going to equal to the angle of the twist of this rod. You guys see that? Because the torque's being pulled over here, so there's going to be an angle of twist from this rod. So there's going to be some like line over here, and then there's going to be an angle, and then it's going to be the same for this one over here. It's going to be the same. You guys see that?
It's gonna be the same angle, or they're gonna be equal?
Yeah, it's going to be the same angle of twist. Okay. All right. Because there's only one torque in the middle. So if you were torquing this again, like if you torque rod BC, then they wouldn't be equal. But since there's only one torque, they have to be equal. So, all right. So you don't need that anymore. Okay. So the angle of twist of rod BC is equal to the angle of twist of rod AB. Okay, so this is what you have to get from mechanics and materials. And the combination between this and this, you could solve for the torque. Okay, because we know this. This is T. We're using rod BC. So which torque is this? This is torque C. So TC L over J. This is for rod BC, so I'll call this BC, BC, and G for BC, and that's for S, okay? This has to be equal to TA L BA over J BA times G BA, okay? All right, notice we have TA and TC in this equation. So we have two unknowns, two equations we could solve. We know this. So we could use statics, substitute the statics into the mechanics of materials equations, and then you could solve for the torque. So you could rearrange this to solve for TA, I guess. Doesn't matter which one you solve for first. You have T, which is known, this T is known, minus TC. So you could stick TA into here. Okay, and then you'll have one unknown, BC. So you have TC L BC over J BC G BC. That's a lot of BCs. All right, and you got T, which is known, minus TC. So I'm substituting that into here. This is LBA over JBA GBA. Okay, so now I don't have to rearrange this whole thing. You guys get the point. You could solve. You can move this over. Whatever. I'll just do it. It's not that hard. Okay. All right. So you have this equation. You could rearrange. So you have TC LBC over J BC G BC. And then I'm taking this part and moving it over, because this is minus TC. You guys get the point. So you can move this over. This is TC LBA over JBA GBA is equal to T, this is known, LBA over JBA GBA. Okay, so from this I went to here, and now we only have this unknown. Everything else in this equation is known. You know the length of BC, you know the length of AB. It's given in the problem 18 and 12. So you can solve for TC. So you can factor this out, divide by this whole thing over here, and then you can get the torque for C. After a lot of algebra. Okay. So the torque you get for C is 9.52 kips times an inch. You guys know what these values are equal to, right? I don't have to plug them in. Yeah, you just get it from that thing. Okay, so you get this torque, right? So now you can go back to the statics and you can solve for TA. So TA is equal to 2.98 kips times an inch. Okay, so now we have the two torques. They want to know the shear stress in each rod. So now we can get the shear stress in each rod. Okay, can I erase this? Okay. Just make sure it's still recording, is it?
Yeah.
Okay, cool. Alright, so now that we got the torques, we could get the shear stress and rod, oh shit, it was BC. I forgot. Okay, this is TCR over J. And, what was that radius? It was the diameter was 2, right? So the radius is 1 inch. So we know this, we know this, we know this. All right, so the torque in BC is equal to TR over pi over 2R. And I'll call this BC because, I mean, it's BC. The fourth, all right, these cancel, so you get the torque. The shear stress in BC is equal to 2 times T over pi R BC to the third. Okay, and RBC is the diameter over 2, and the diameter we said was 2 inches. 2 inches, so this is 1 inch. So we know this value, we just found this torque, this is C. Okay, so we know that value, you can stick that in here and you can get the shear stress in rod BC. Okay, so this is 6.06 KSI. And then you could also do the same thing. You can get the shear stress in rod AB. So the shear stress in rod AB . Okay, so tau AB is equal to 2 times TA over pi RAB cubed. Okay, it's the same formula, except the radius is different. The diameter they give you is, they give you 1.5, so the radius is 0.75. So this is 0.75 inches. We know this, we just solved for it, so you could get the shear stress in AB. What was this? This was like 2.98, right? Yeah. Okay, yeah. So this is equal to 4.50 KSI. Whoops. These are your answers for A and B. Yes.
Earlier, pi is 5 BC equal to 5 AB, like the angle.
Oh, I was explaining that before. Why are the angle of twist equal? Because there's a torque in the center, and the angle of twist has to be equal for each rod. They have to, or they're gonna separate. Like, if they weren't equal, then that'd be a problem. So, yeah. Any other questions?